All right, let's talk about another crystalline imperfection, and that is the interface, or two-dimensional imperfections. So what would this be? Well, an imperfection is a disruption in the regular repeating arrangement of atoms. And so there's a few different types of interfaces that we could look at. Let's look at the first one, and that's a free surface. So here what I've done is I've drawn just a simple cubic lattice, square lattice, I guess, in 2 dimensions of little atoms, okay? Now, what if we said, somewhere they hit a surface, the edge of the material, like the edge of this chrome finish on this little clip here, for example. Well, then all of a sudden, there's an interface between the material and air. That's a disruption. There's an atom here, 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 and so on, in a regular repeating arrangement, and all of a sudden there's nothing. And the atoms at the surface actually have fewer nearest neighbor atoms. They have, another way of saying that is they have unsatisfied bonds. Doesn't that sound terrible? Unsatisfied bonds. And so there's an elevated energy associated with that. Elevated energy. In fact, we have a name for that, and that energy at this free surface is, you guessed it, the surface energy. Surface energy. Okay. In the case of water, you might call it the surface tension. In fact, I thought I'd try to do a little demo here. So here's a piece of glass, and you've probably seen this before. If you have ever seen some, water coming down, as I'm sure you have, the window of a glass enclosure on a shower, or rain coming down a window at your house, and coffee. So why am I doing that? Well, I thought that would be kind of funny to put some coffee on here. I was hoping that the brown of the coffee would show up. I don't know how well it actually does. But what I'm trying to illustrate is what happens when 2 drops of, thankfully it's not too hot, my coffee come together. Now, I don't know if you saw it there. Delicious. The 2 smaller drops came together and formed 1 larger drop. Okay? I think you know that to be the case. Why is that? Well, because 2 smaller drops, it's a drop, and here's another drop, perhaps a larger one. I'm trying to give it some shape there. Okay, this one comes down, and what happens is you end up with 1 larger drop. Looks like this. Okay, larger drop. So initially we had actually 2 drops, didn't we? And then when they contacted each other, we had a larger drop. Why is that? Well, the reason for that is there's lower energy in this system. Specifically, for 1 large drop, there's a lower surface area to volume ratio. For the same volume of material, there's less surface area, there's less surface energy, and that's a result that you've probably seen several times before. So another thing I want to look at is, well, what if this interface here was not a free surface, as this one is? I'll label that. So we've got that. That's a free surface, but an internal surface. Okay, an internal surface. Let me give myself a bit of room here. Okay, what about an internal surface? And what I'll do is I'm going to add, I'm going to discuss formation of a crystal. So here's a little lattice. I just wanted to demonstrate this concept here. And we got some atoms moving around in the liquid state, moving really quickly, and eventually what happens is a few of them slow down, and they start to cluster together. And you get enough of them together, it forms a critical size, and they start to grow. And this crystal will kind of grow. It's a bit of a simplified look, but it'll get bigger. More and more atoms in the melt will slow down and deposit on the surface, right? They'll form metallic bonds. They'll achieve a decrease in energy by doing so, and so on. But the other thing that'll happen is elsewhere, that exact same process will occur. Let's just put this crystal over here somewhere, perhaps, and that crystal or grain will be oriented at some different orientation. Okay, it's a different orientation. It's just random, the orientation that it might have, and I'm going to put it together. And so what happens when they come together? They hit each other, and the atoms don't line up properly. They don't line up exactly, and so right in here we have a boundary. It's a two-dimensional boundary, and it's a boundary between what? It's a boundary between two grains. Okay, or the technical term is grain, but it's actually synonymous with crystal. Okay, but we're going to use the term grain as that's what's commonly used in this context. So what do we have at that interface? Well, just like we saw previously, we have an elevated energy. We've got unsatisfied bonds. We've got a little bit of mismatch here between the atoms. They might be a little closer than they should be, a little further apart. And so one example I want to take a quick look at is, well, what would happen then if I had a dislocation moving through the lattice? So there's my little symbol for a dislocation. I'm not going to draw the actual dislocation in, but that would move, it would proceed through this crystal, and then when it hits this crystal, it has to change direction. Okay, it has to change direction. And so that change in direction, if we just want to think about mechanical properties, a dislocation that encounters the grain boundary must change direction. Okay, what does it have to do? It has to change direction. That takes some energy. Direction. Okay, change direction. Give myself a little bit more space here. That up. It's going to change direction. It's going to have to navigate a planar mismatch. That is that this, this particular plane that the atoms are sliding on might not match up exactly with this one. So they'll make a little step like this. One's coming here like this, and then it doesn't quite match up here. It's got to make a little step. So that takes a bit of additional energy. And there might also be some lattice strain that it has to navigate across. That is, the atoms are not at the regular repeating interatomic spacing. They're maybe a little bit closer together or a little bit further apart. And it has to navigate all of those. And for those reasons, we can make this statement: the grain boundary inhibits dislocation movement. Okay? Dislocation movement. And why is that important? Well, that's important because all we need to do then to strengthen a metal is decrease the size of the grains. Decrease metal, strengthen metal by decreasing grain size. And there's various ways to do that. But all else being equal, two samples, one with fairly large grains and another with kind of smaller grains like this, and I'll spare you the agony of seeing me draw all these little grains in, okay, but small grains like this, that dislocation would have to navigate, say in this case, maybe three grain boundaries. In this case, it's got to navigate all these different grain boundaries. There's more grain boundaries, more grain boundaries. So what do we see? Increase in strength. All right, fantastic. That's a two-dimensional imperfection. Thanks a lot.